Hi friends, welcome to everyone B for Engineering. Today we are going to discuss about the Phasor diagram of an actual transformer and equivalent diagram of actual transformer. Let us consider this is a transformer. There is a primary winding and secondary winding. What we are going to do? We are going to connect the primary winding to the voltage source V1 and secondary winding is connected to the load. Connected to the load. Suppose we connected a voltage V1 source in the primary side, we know that there is a current will pass through the winding, that is we can recognize I1. Now two components. One is once we pass a current through the winding, there is a resistance value will be in the coil. At the same time there will be a inductive reactance also. That what we will do, we will take resistance value R1 and reactance value X1. These two from this coil, we are for the calculation purpose we are taking it outside. That means the resistance value of this coil we can represent it as R1 and reactance value of this coil is X1. Now we will get again this is I1. Now this I1 current will passes through the coil. Then as per the thumb rule, if a current passing through the coil, this current is passing like this. If a current passing through the coil, there is a flux will be generated in the direction of thumb. That is this direction, there is a flux will be generated. But once we are applying current I1, this I1 will be used for generating the flux, and some flux will be lost surrounding the air and some flux will be lost due to some other losses. There are mainly two losses. One is eddy current, another one is hysteresis loss. This is two no-load losses. What is the meaning? Once we are applying this current I1, this current is utilizing for generating the flux phi into the core. At the same time, it will be some amount of current will be lost due to eddy current and hysteresis loss, or we can say it is a constant loss. Then what we are doing, this constant loss is proportional to this voltage, that we are taking it out. There is a eddy current loss. Eddy current loss we will represent in the inductance, because eddy current is depends on this flux. This flux is changing nature. It is a sinusoidal. And there is a hysteresis loss, that is always a constant. You know that one is a constant. That we can say this is X0 and this is R0. There is a current for magnetization I mu. For the no load condition there is a IW power current, for current. These two current will be flowing through this for hysteresis loss and eddy current loss. Then by adding these two current we will get I0, no load current. Then we can say this is the current of I1 dash. That means actually we are using I1 dash only for the transformer function. Balance everything, balance this current I0 current is separate from the constant loss. Then after removing these all things, we will get a voltage E2 here. E2. Then this flux will be passing to the secondary side of the transformer. It is a rate of change in nature. It is in a sinusoidal way. What will happen? This flux will be linking to the transformer. Then there is an EMF will be generated in this winding, the voltage will be depends on the number of the turns of the coil. Then what happens? There is a voltage. Leave all the list. Then there is a voltage E2 will be generated here. Then again we will come to the secondary side. There is an inductive reactance and a resistance in this winding. What we will do, same what we have done in the primary side, same we will do in the secondary side. We will take it outside. There is a inductive reactance and a resistance. We can represent it as X2 R2. Then there is a current will be flow I2. Then this I2 is from I1 dash. Now this I2 direction we will discuss later. But then now this is the equivalent circuit of a transformer. Then we can redraw like this. There is a transformer. There is a secondary side induced EMF E2, primary side EMF E1. Then there is a current I2 dash. There is a no load component of I0. Then R0. Then X0. Again come outside. You will get the X1. Then we will get R1. There is a loss across the inductor, that is I1 into X1. This is I1. There is a loss in the resistance, that is I1 into R1. There is a supplied voltage is V. This is the primary side. And if you are coming to the secondary side, there is an inductive reactance, there is a resistance, then a load. There is a load. This is X2, this is R2, voltage across this one, this is I2 into X2, this is I2 into R2. This is the equivalent circuit of transformer. Now we are coming to the phasor diagram. Now what we are, any diagram, whatever we want to take a base value. Suppose we are taking the base value as a flux phi. Then EMF induced in the secondary side E2, that we can write as E2 is equal to d phi by dt. If it is a derivative value E2 will be lags the flux by 90 degree. This is E2. Then we know that all the losses we will take it outside. Then it is a purely without loss element. Then we can say E2 is proportional to E1, or E1 is equal to the phasor value E1 and E2 is equal in phase. E1 and E2 equal in phase. No, it is not exactly happen, but this I will tell you one thing. If the current is moving, this direction, then there is a flux will be generated in this direction. Am I right? That is, flux will be in this direction. Then now it is coming to the secondary side. What happened? The flux is in down direction. Because of this flux, there is a current will be generated in this direction. That means it is in this direction. Then ultimately current will be for this is actual I2, then this is I2. Then this voltage, we can suppose this is plus minus, here it is minus plus. That means E1 is exactly opposite to the E2. That we can write it here. This is E1 dash. Now again come back to the primary side, and we are going to write these elements. Here we know that the current I mu, this is current I mu is a magnetizing current. This is depends on the flux, then it will be in phase with phi. This is eddy current loss because of the field existing from the core. And there is another component, this I1 and R1, it is in phase with the voltage, because it is purely resistive. That we can say this is IW. Then resultant of these two vector, we will get no load current I0. This I0 we will get. Okay, now I0, we get the I0. Then what will I1 is equal to, leave it. Now it is come back to the secondary side. Now what? But we want to find out I2. Here we can say this is I1 dash. This is I1 dash. Then I1 is the resultant of I1 dash plus I0. I1 is equal to I0 plus I1 dash. The I2 is in phase. I2 is in phase with the, but is in opposite nature because the current is going in the downside. The direction is different direction. That is, I2 we can write exactly opposite to the I1 dash. This is I2 because flux, now the flux current is moving like this, flux is going like this. Now flux is going down side, then current will be down, then it will be in the downside current direction will be a downside. That is, it is exactly opposite to I1 dash, is exactly opposite to I2. Now then we will come again back to the output voltage. This output voltage we can write it as V2. Here also it is V2. Then what we will write is V2. We will write, there is a voltage. We are coming from the secondary side to the primary. Right now we are coming from secondary side to primary. There is a V2. There is a V2. Okay. Then V2 minus V2 plus I2R2 plus I2X2. V2 plus I2R2 plus I2X2 we will get E2. E2 will get, once we adding drop across the secondary side resistance and reactance, then we will get E2. We can say secondary side resistance drop I into R2, I2 into R2, that is always in phase with the current. That is, maybe we can write it, this is I2 R2, and we are taking this this is I2 R2 in phase with current I2. Then this vector we are taking it from here and keep it here. This is I2 R2. Now there is a vector I2X2. It is lag to the current, or it is a lag to the current, or lead to. It is lead to the current because I is equal to V is equal to di by dt. V is equal to d. Similarly, what we are doing, that when E is equal to d phi by dt, if flux is a reference vector, E must be lead behind the flux by 90 degree. Lags behind the flux by 90 degree. Here also, there is a drop across the resistance, lags behind the current by 90 degree. Then current is I2. Then we can say this I2, we can write it here. It is 90 degree. This is I2 X2. It is 90 degree with current. Then we'll take this vector to here. This is I2 x2, then what we will get E2. That means E2 is equal to V2 plus I2R2 plus I2X2. E2 is equal to V2 plus I2R2 plus I2X2. Now, then come again back to flux phi. We are get phi, then we are getting I1 dash, then summing these two I1 dash and I0, we will get I1. That is because it is a parallel running, that is also E1 dash. I want to use this one E1 dash. Now what we are doing, then V1 is equal to E1 plus I1 into X1 plus I1 into R1. Then I1 into R1 is in phase with I1. It is in phase with I1. That is, this is I1 into R1. We will take this vector and adding here, we will get I1 R2. Now there is I1 into X1, that is 90 degree. That is 90 degree means I1 is here, this is 90 degree. This is I1 X1. Take this vector and keep it here. This is I1 X1. We know that E1 plus I1 into R1 plus I1 into X1. E1 plus I1 into R1 plus I1 into X1. We will get supply voltage V1. And this is the phasor diagram. Hope you like this video. If you are like this video, please like and share it to your friends. And still you are not subscribed my channel, please do it now. Thank you. Have a nice day.